Welcome again in today's lectures about computational methods in mechanics, session number 3. Let's me start sharing the screen. And today we will continue our talk mostly about numerical integration with two subtopics. Firstly, we'll discuss about just computing those integrals using numerical approximation methods. We'll use two methods, a composite trapezoidal method that we have deal with last time on this theory basis, and we'll use midpoint rule. And then another slightly, I think maybe even for today, bigger topic will be about testing. Testing, we'll get back to floating point numbers and things like that. Okay. So, by the way, I have received a complaint from one of your colleagues. Of course, this is understandable. About that we are going too quickly with the topics during the lecture. And particularly that I tell that this is simple and we can go on. So, okay. So I will start. I will try not telling this because this can be discouraging. I know that not all concepts that are shown here are simple. I use this phrase mostly to check about the audience that it's here that might or might not have complaints about complexity and if we can go further. And I think this is particularly can be hard for those students that have to work full time and cannot attend those lectures live. However, if you have any issues with assignments or any additional comments regarding to the lectures, especially the parts that I skim over, I really encourage you to contact me. Then we can just maybe meet in person or meet in Teams to discuss those things. And I think that this could, help quite a bit. Okay. Any questions? Can we continue? Because today we start with this slide. I think that this was one of the latest. It was already shown. I'm pretty sure that we discussed this in details. Last times. I'm bringing it back here because there is the algorithm. So this shows the general algorithm for composite trapezoidal integration. And it shows all those three main steps. Okay, here at least I have those options. So it shows three main steps. So the first step is to use the properties of the integral to divide the integral over the full integral AB to smaller intervals. That are indicated by those x's. And of course xo is equal to A and xn is equal to B. And we just slice it into smaller pieces. And then here is this approximation step that allow us to compute it numerically. And this approximation step tells, as we discussed, to divide all of those small slices treated as small and small trapezoid. So here we have the just basic equation for how to calculate the area of this trapezoid over the small interval. And because we have here intervals with constant width, h, that's why h appears here. Two next steps, 3 and 4, are about the transformation to put it into algorithmic form. So firstly, gather the common term and then use summation. And with this, we get this equation at the end, h times f at first point by 2 plus f at the last point by 2 and summation over the values of the f in all the intermediate points. For this, now we have algorithm. So for warm-up, we have this hands-on. And also, for clarity and also for information, to myself, yeah, I start putting this Q here, yeah, that indicates that, yeah, there will be quizzes related to this. There will be some quiz related to this slide, yeah. So also, I'm not using MATLAB online because I couldn't change the size of the font. We will use standard MATLAB, but we have this Socrative system. Damn it. Of course, that we will soon use, yeah. So then I don't know what should be. Shuffle questions, no. Shuffle answer. Teacher pays because it's like that. Yeah. But before we will get there, here we have this hands-on. Yeah. So in general, this code, yeah, because here you have equation, yeah. So the task here is to write a function called, for example, trapezoidal, yeah, that takes 4 arguments, f, a, b, and n, yeah, and return the approximation of the integral using the equation above, and maybe to write a simple test that will check if your implementation looks anyhow correct. Yeah, this function can be written in like 5 lines, yeah, maybe 6, yeah, because you need a header, then you need some initialization. You have to take care about those 2 terms. Then you have to write a loop with summation above all the middle steps. You have to calculate somewhere h, yeah, and then run it and return the result. Okay, is it clear what is task here? And is it clear how to implement this function? What is unclear? You have to write function with this header. Yeah, so function area equal or integral equal to trapezoidal FABN. And what is F? Yeah, exactly. F is a function, like in this equation, function F. Yeah. What is A? The lower limit. Yeah, exactly. So A, B, and are limits of our integral, and N. Exactly. Number of the trapezoid that we use, number of dividing point, and number of those smaller intervals. Yeah, and it's used here, for example. Yeah. So with those meaning, yeah, and the task is to write a function, trapezoidal, that will just implement this equation. Is it clear how to do this? Okay, so let's take a few minutes and try to implement this. Later, I will show you example implementation. Yeah, and then we'll can start a quiz. Okay, are there any questions online? Okay, no questions online. If you have any questions, feel free, of course, to unmute and speak out loudly. And if you want to show me some code and have questions to it, of course, I think it's also, possible through Teams.
Yeah, it's just.
Yeah, correct.
They're using that.
Yeah, correct. Yeah, but
So that's why it's not what I.
yeah. But don't use zero.
Isn't the CLC basically the same?
Is
Yeah,
yeah, but they have different environment.
Yeah, but
Yeah.
it follows the same CLC and zero.
No. It's totally different. CLC just clears secure.
Yeah.
And clear all clears your variables, caches, global variables, your code compilation, and many others. So it's typically harmful.
Yeah, it's yeah, if you're going to like.
Yeah, I'm extracting your computation.
That's as expected.
Yeah. Okay, I don't know, green.
It should be the same more or less.
Yeah, it's the same. Yeah. Because I'm not so fluent to know 100% sure how it works at the Socrative yet, but yeah, it seems that the room is the same, so I think it will be all the time the same. Yeah. Syntax.
And deal with this kind of evil.
Yeah, I'm sure. I have the same issues with like different one. What do you use clear all? What do you want to clear? Why do you use close all?
Yeah, I always
Tools or
So can you stop doing this?
it's a problem.
Yeah, at least do not clear all. No. Okay.
they're almost done.
The question?
No, and it's a great job.
Okay, so do you want me to show how I would implement it? Okay, I would implement it just the way you did, yeah. But it seems that some of you are struggling with the implementation, so do you want to see some example implementation? There are many of them possible, of course, yeah. So, or do you just want to see ready code? Okay, it's so short, yeah. Let's implement this. Damn. So, as we describe your computing function, yeah. Yeah, the header was provided for us, yeah. So we will return value of the integral, yeah, and we call function trapezoidal, and it takes those 4 arguments. Let's save it. Yeah, and yeah, we have to calculate and implement this function directly. Yeah. So the first thing that we need is age. Yeah. Age is equal, I think it was on the one of the slides, is the length of the interval. So just b minus a divided by n. Yeah, just standard equation for the length of the interval when we divide into the constant size intervals. So this is done. And then next we have to deal with this expression into brackets. So we have here two free-form elements that you have to take care as separately. So, and we use those two to initialize the value of the integral. So the returning value. So if it's f of a plus f of b divided by n. No, by 2. Is it correct? F of a divided by 2 and f of b divided by 2. So we take care about those two endpoints. And next we have to calculate this for loop here. So one way is to write it simply as it's written here. So from 1 to n minus 1. Because it's from 1 to n minus 1 according to the equation. And then to calculate it, for sure we need to calculate xi. So xi is, what is xi? What?
A plus I
Oh, yeah.
times H.
Exactly. A plus I times H. Because those are the following points. It doesn't matter in which direction we calculate them, it's summation. But this is the most obvious and not wrong. So this is how to get all those points. And it should work because the first one is A plus H, and the next one is just one before we hit B, And now we can write that integral is integral plus f of xi, Does it make sense? So okay, so now we can see the equation and the code in the same screen, And we can see that, we have h, we have this term, it's here. This last term is just here, fb by 2. And this middle term, that calculates all the summation is just implemented here. No fancy stuff. Is it okay? What is missing? Exactly. Exactly. So you are following. So now we have to do the last step. Because all this, we calculate with this integral in those lines from 5 to 10, we calculate what is in those brackets, square brackets. But to make it complete, we have to multiply it by h. Okay, and this should be ready-made and okay calculation for the trapezoidal rule. Now, of course, we are not so trustful to ourselves, that there still can be some small errors, So let's write a second script. And this script is this script is to make a basic test about trapezoidal, So trapezoidal check, and here we have some example provided, So firstly, we need this function, So I will just make this equation for anonymous function, So it's function of t, and it's 3 times t squared times ax pair of t to power 3. Yeah, and f, or we can call it v. I think it will, yeah, according to the slides. And v is our anti-integral, antiderivative. Is just exponential t to power 3 minus 1. Constant is not so important, but and now we have to select a and b. A equal to 0, so we start at time 0, yeah, and b equal to, for example, 1 second, and let us use 101 points, because why not? So we use this example and we tell that v can be, for example, some velocity of the car, yeah. So so then the integral will be distance, yeah, and numerical value of the distance will be calculated using trapezoidal rule, yeah. So then we have trapezoidal. First argument is function, so v, and then we have I think it should be rather t0 and yeah. So the lower boundary is t0, the upper boundary is t end, yeah, and n is just the number of divisions, yeah. Also, we can calculate this distance using an analytical approach, yeah. So we calculate v of t end minus v of t0, yeah. And now we can just display both values. Yeah, and let's see what will be the result. Okay, close enough? Okay, perfect. And now we have our quiz. Yeah. Simply for you to run this trapezoidal for yourself, yeah, and check what is value of the exact function that I have used in this test, yeah. From 1 to 2, yeah. So we calculated from 0 to 1 seconds, yeah. We are using 101, yeah, but here is just to use 3 steps, yeah. So 3 rough integrals, yeah. Then the question is, you know, what is the answer, yeah. So yeah, you need MATLAB to calculate this and follow the code. How it's on the other courses? Someone check the answers or check if you just take part in the quizzes? Hmm?
Dynamics, it was just at the same. It's like for additional nutrition.
Okay.
And like what you want to do, like we just want to like let people just get points by basically being here. Like say encouraging to be here, or do you want them to actually also get the right answer? But I'm not sure.
Okay. Yeah, because I was thinking just to give points for participation, because yeah, those questions can be sometimes tricky. Yeah, and I think that this is what matters, and still the main mean of evaluation is about assignments. But okay, so because this is the first one, let's give maybe an extra minute and then we'll move forward. Okay, are there any questions from anyone? Okay, not really. Yeah, 10 seconds. Okay, done. Let's see. Okay, so quite few get the correct one. Okay, yeah. I already put the next question. So I have to, but okay, yeah. We have, by the way, short discussion about this specific or this always shows here, yeah, about this kind of specific or general implementation, yeah. And so we are discussing that it's, that function with those general implementation provide us a certain level of abstraction, yeah. And despite this concept is pretty challenging, why it should be used, yeah. So again, yeah, one of the main reasons for this kind of abstraction is that we have this reusable functions, yeah, that like we implement these trapezoidal functions and calculate, for example, this distance, then it can be used in any other code, yeah. And typically, well, you will learn that when you get experience, hopefully, that as you write something, it's not the code that you can just trust easily. Yeah, there's a lot of places where it's super easy to introduce any kind of the errors of different nature. Yeah, and RAF is simply complicated. Yeah, so if you have some function, especially if you start to test it, yeah, you get into the approach that you get simply less errors. Yeah, so it's easier to write, easier to compose, easier to read. Yeah, and you don't have to remember all those details that are there. So these hidden implementation details are typically pretty important. Yeah, because after you get back to your code in few weeks or months, yeah, it's hard to remember what was there. Yeah. So writing function is very good habit and good skill in programming. And we will write about many of them. Yeah. So now we are getting to next method. Yeah. So we just have dealt with composite trapezoidal rule. When we have those intervals, we replace them with those trapezoids. Yeah. And now we have composite midpoint method. Yeah. In short, is typically called midpoint method. Yeah. So in midpoint method, instead of using a trapezoid based on the value of the points at the ends of the intervals, we get the value of the function in the middle and approximate it with a rectangle. Does it sound like a good idea or a bad idea?
Like small, maybe.
Okay. As it's written here, this method is typically more accurate than the trapezoid. Yeah. So it could be a good idea. Yeah. And the reason is that, take a look, if you have here some kind of trapezoid, yeah, in practice with this trapezoid, by having this line, you are trying to figure out based on the endpoints, what is the average of the function. Yeah. And here you are just probing average directly. Yeah. So for most functions, yeah, of course, there are always exceptions. Yeah. But for the most functions, yeah, in general, this method will be more accurate for the same number of divisions. This difference doesn't have to be huge because they have the same convergence properties. Yeah, they are still pretty simple. Yeah, but yeah, what is the main disadvantage of this method? Is there any you can think of?
And that's the very line.
Yeah, of course, but this is the disadvantage. So yeah, the comment was that that if the line is super curvy and we have not enough steps, yeah. But this is for all approximation methods, yeah. So it doesn't matter. Yeah, you can always, with this, if you have super curvy and then very rough steps, yeah, and all those will fail. Yeah, then you need you have to check the convergence. But this is other. I was thinking about something else. Yeah. I was thinking about practical applicability of this method, especially when you have the measurements. Yeah, because this is one of the very popular way. For example, even if you have some simple PI controller, yeah, then you have to integrate the stuff. Yeah, or just you have some accelerometer and then you want to get velocity. Of course, it's not so easy, but let's say that this is the case. Yeah, when you have trapezoid, you are getting points and constant intervals. Yeah. And then you can just use trapezoidal to integrate it. But with the midpoint rule, you need value in the middle. Yeah, that typically is not there. Yeah, for measurements, you typically get it. Yeah, at the boundaries. Yeah, so it's not directly applicable. But okay, like with all the methods, they have some applications and others. But still, here is the method, and here is just the example, yeah, how to calculate it with also four integrals, like here from 0 to 1 VT, yeah. Simply, it's wide, yeah, so one side of the rectangle, and the next is value in the middle, yeah. So it uses even one less function evaluation. And yeah, and for our example, it's slightly more accurate as it's shown. Okay, so then we have a general algorithm, but before that, we have those two quiz questions here. So first one is, what is the key feature of the midpoint rule for numerical integration? Should I read the answers? I think that you can read them by yourself. Okay, let's give extra 10 seconds. Yeah. And next one. I hope it's easy. Yeah? Which method is generally more accurate? Generally, not always. More accurate for a smooth function, the composite trapezoidal rule or the midpoint rule? There should be timer here. Do you know if there is timer?
Yeah, like because you have set the teacher driven, there is no timer.
Oh, okay.
So, you could maybe like open like some kind of website next to it and just have like a self-made timer.
Yeah, well, I have clock, so it's not crucial, let's say. Yeah, but okay.
1 hour to see like maybe just on the right next to it.
Okay. But yeah, as we discussed, in general, it's midpoint rule that is more accurate. Yeah, of course, it depends. Yeah, but in general, it's midpoint rule. Yeah. And then the question is also about implementation of this. Yeah. So here we have the general algorithm for midpoint rule. Yeah. Just written in the way that it's reasonably easy or easy to implement. I believe that after the trapezoidal rule, this should be already pretty easy to implement. So the first step is exactly the same. So the first step is just to divide into smaller intervals of the constant width h. Yeah. The next step, again, is approximation step where we use the values of the functions in the middle. Yeah. So that's why we are using like middle point. Yeah. And that's why the name midpoint rule. Yeah. So using the h times value of the function at the midpoint. Yeah. Next step is to just get common terms. Yeah, here h is we can just take h outside of the brackets, and the name is to find the pattern for summation. Yeah, and pattern for summation is that one. Yeah, so it's even slightly easier than trapezoidal rule. Yeah, because here we have just simply summation from 0 to n-1 of f of xi. Xi now the difference is that it's just middle point, not the point exactly at the interval points and the interval ends. And as you can guess, your task is to implement midpoint rule with the same header as trapezoidal function, just the name is different. Equation is slightly different, and the task to be checked is exactly the same. Any questions? Now I hope that it's even more doable than the previous version. So I will give you a few minutes to try to implement this. And let's check if we have any questions. Okay, let everybody knows that they are recorded and transcribed. So you are recorded and transcribed. There is no questions. Okay, everything seems to be fine. If you have any questions, let me know.
Yeah.
Okay. So this is always the struggle with the problem. That's and some kind of solid has to be searching. This is for one. And so that's why I mentioned that, especially if you use function, at least if you use this function for some time, yeah, then you will start getting to be sure that it works properly. That's the nonsense. Yeah.
Ability for still have the entity. But I can just go on to like two ball elements.
You mean that in this one, you don't need this.
Page of the page. So obviously.
It is very good plan for but okay, I don't complain too much because it's something it is very serious. So it's it's good. But also integral might not be also the best that I use because it's also negative functions.
Next time.
Yeah. Okay, it's not a big thing, something especially. You have syntax approach using functions and those steps.
Is the number of steps or the size? This is the steps. And this is the number of steps. Yeah. And also is the size of the steps. Yeah, but in here should it be the size?
What the numerical me you get. Yeah. Then you get what you can eat. What's the integral of the distance?
Somewhere about it. If you use the estimate from the slide zero, because otherwise the A makes no sense. It's not many times you all be at this assumes you like the first line is.
Yeah, it's here. And then the integral of the distance over time.
This would be nothing.
Yeah.
And after the rest and this. If you not listening behind, okay, you start with A, H steps. If you look down, you start to be able to.
Okay.
It's all exile, it's the. E zero, the first step.
No, not that one.
A is here. Again. So that's the step.
Okay, still no questions. Okay, so at least here in the classroom, it went pretty well. Yeah, the implementation. So most of the people here were able to implement it based on the trapezoidal rule. Do you want me to show the implementation just in case? Okay, so implement it. I would just not always this is a good point, but because of how similar they are, I would copy paste the midpoint. Yeah, so this could be the same. This doesn't make sense. Yeah, this must be 0. Yeah. Because we just have summation, yeah. So then we have to implement this loop. So we have to check the indices, and the indices are from 0 to n-1 exactly. Then it's important to remember that xi changes, yeah. So it's a plus h over 2, and then okay, of course, this is not needed. because it's just summation h plus a plus h over 2 plus I times h, yeah, to get the points. And then, yeah, this is the same because we want to sum up all the values of the midpoints, yeah, and then we have to multiply them by h. Yeah. Any doubts, questions? So now, the second point was to test your implementation. Yeah. So to test implementation, let's do the same because the majority of the code will be the same. So let's give it here. Yeah. So script to quickly check point M. Yeah. So those are the same. Yeah. Function and its antiderivative. Those conditions are the same. So, and the only place to check is here. Instead of trapezoidal, we are using midpoint. And now all the things are met. And if there are some silly mistakes that are super easy to do. Yeah. And as you can see, also on this example, midpoint appears to be slightly more accurate than trapezoidal, because here we have results from trapezoidal. It differs by maybe not huge value, but still 0.003. Yeah, and this differs by just 0.002. Yeah, slightly better. Okay, and I think that we can, you should have this answered, or so I would just give you like half a minute to finalize the answer. Yeah. So the task is very similar, like the one from the trapezoidal. That now we just use midpoint rule. Yeah, and instead of 2, 3, you have 0.1 to 0.2, and just with 2 steps. Okay, half a minute has passed, so let's see the results. Quite nice rate for good answers. Nice. Okay, some quick final answers, and let's continue. Yeah. The next question, if you have seen, it's about rounding errors and floating point arithmetics. Yeah. So here I have the one short hands-on, yeah, to compare both methods and to print them nicely. Yeah. But that one, okay, do you consider it anyhow challenging? Yeah, this task. Because I'm that write a program to compare both method, trapezoidal and midpoint. Yeah, here is function, and so the definition how to call them, and then the task is to call them for the points n equal from 2 to 20, to the power of 20, and then print them nicely to compare. Does it look challenging? Is it okay for the homework, just home exercise? Or you want to solve it, or you want me to solve it? Hmm? So do you want to solve it at home? Okay, perfect. Yeah. So again, if you are struggling with tasks like that, let me know, and then we can, I think, consult and discuss what are the issues, and I can direct you to some solutions, to allow you to develop your programming skills further. I think it's pretty good task for this type of goal. Okay, so we are done about integration. Yeah, there are some extra topics in the book if you are interested, like Monte Carlo integration, double integration, others. There are a lot of numerical integration methods. Yeah, there is Simpson's rule. Yeah, that instead of those lines, use some cubical splines, if I remember correctly. There is Gauss quadrature. It has slightly different goal and slightly different structure because it's for analytical function. Yeah, its nice properties is that for properly defined Gauss quadrature, we can exactly integrate polynomial of provided degree order. Yeah, and it's very nice. Like it's very commonly used, this kind of rule, Gauss quadrature, in finite element methods, for example. Yeah. All of them followed the similar, in practice, the similar scheme, yeah, that you have summation over some weights and over some points, yeah, and they just differs in how do you select those weights and those points. Yeah. There are also adaptive methods. Yeah, I think that you have to deal a little with adaptive implementation of the very simple adaptive method on your assignment. But now we are going to the next topic. It's about testing. Okay. So the topic is that writing tests for the software is pretty easy and straightforward. Yeah. But of course, you know, it's another skill that you have to get used to. And in practice, why to test our software? Because it's super easy to make any kind of mistakes. Yeah. Including the mistakes in just implementation. Yeah. Or at any stage. Yeah. Yeah. You can just put the code in correctly, whatever. Yeah, you want to be sure that your code is working on the way you are wanting it to work, and it's working for example, the settings. Yeah, so if it works for real numbers, if it works for integers, and many others. Yeah. So we have done some tests. Yeah. So we make one of those checking that we compare it with exact solution. Yeah. So, and we just use, there are decreases and increases, that's true. Yeah. But in general, we just use one case on 101. Yeah. It provides us good value. So we were pretty happy about this. That we also check that it stabilizes and grows. Yeah. So this was task of the second hand on that we haven't seen, but if you implement it, you will see that as the number, this n increases, yeah, the values gets closer to the exact value. Yeah. And of course, all the initial digits will remain the same. So that way it will stabilizes. Okay. Unfortunately, those are, as written here, pretty weak tests. Yeah, one of the reasons is that if you want to have any kind of testing, it must be automatic testing. Yeah, so if in the future we make any kind of modification to those methods because of whatever, yeah, we want to improve its efficiency or just we want to revise the file, yeah, and then you make some error there, yeah, it won't be catched. Yeah, because there is no automatic checking routine. Yeah, so if testing must work, it must be automatic testing. Yeah, so that's why there are frameworks. We will use one of the frameworks built in here to make it happen. And of course, there are still some errors that a test might not catch. Yeah, of course, now you can, one case is how do you know if the tests are correct? We don't know. Yeah. We are not sending people to the moon, fortunately. Yeah, maybe you will. Yeah, then you will have to go through far more rigorous testing routine. Yeah, but here we're just calculating some integrals. Yeah, velocities. Yeah, hopefully nobody will be harmed if there are some inconsistencies. Yeah, but in general, you know, it just provides some extra safety to the code. Yeah, if you have tests and you have the code. Yeah. then hopefully they together will match and provide better code. Yeah. If you will find in the future that something is off in either of those, you can always go back, revise, and yeah, or write extra test for the cases that you haven't considered at the start. It's pretty typical. Yeah. If you work on the package, it grows not only functionality, but also the test side grows. Yeah, and usually the longer we use the procedure, the more we can trust it. Yeah. There are, for example, very simple errors that can be introduced to this code, like for the trapezoidal rule, that are very hard to catch. Yeah. For example, likely if we use high n and we just use incorrect indexing, no tragedy would happen. Yeah. Or if we would forget about this. Yeah. Still, it could show like convergence properties. Yeah. Especially here, if we totally omit this part, nothing would happen for our test case, because in our test case, it starts from 0 at 0. Yeah, so there are typically better ways to do this. Yeah, and before we will get a little into testing, here is the question how to write the test. And to write the test and to write automatic test, we need to make automatic number comparison. Yeah, and it seems that it's not so obvious. Yeah, so what was shown there? Yeah, that if we write 1.2 equal to 3, this kind of expression? Do you know what I will get when I will hit return? Yeah, I should get true, because now I make comparison. Yeah, logical one. Yeah, it doesn't maybe look the prettiest one. I would prefer to have true here. Yeah, but that logical one is true. Yeah, and now what happens if I do something like that? What I'll get? Is it true or not? You can check it by yourself. But we get the information that this is false. Is it something that you are expecting to get here? Kind of yes and no. Yeah. So why it shows that it's false despite it looks like it's true? Any hints? We already discussed this, but it was some time ago. But the key reason for this is because of the floating point numbers representation and the fact that they are not accurate. Yeah. Yeah. So I have even some two quizzes about this. Yeah. Yeah. So real numbers cannot in general be exactly represented on a computer. This is the case. Yeah. So let's get into quizzes. Yeah. Why do rounding errors occur in floating point arithmetic? Yeah, because this is because of those rounding errors. This is the nice name for this. Because floating point numbers can only represent integers, because floating point numbers have finite precision and cannot exactly represent all real numbers, because floating point numbers use a decimal system, or because computers have unlimited memory. And no more coffee. Yeah, but that's fine. Okay, 20 more seconds. Okay, so the time is done. Yeah, yeah, exactly. Because floating point numbers have finite precision, and cannot exactly represent all real numbers. What is the potential impact of finite precision on numerical computations? I think this is the hardest question for this series. It can lead to exact results in all cases. It can cause small errors to accumulate, leading to significant inaccuracies in calculations. It only affects the speed of computation. It only affects the storage size of the data. Maybe extra 20 seconds. Okay. Yeah, almost perfect. Exactly. The errors can accumulate, and yeah, this can provide some inaccuracies in calculations. Okay, perfect. Integration is nice because those accuracies do not have tendencies to rise, yeah. And also, this is the reason why MATLAB, for example, uses double precision numbers, because of course there are also single precision numbers, yeah. But single precision numbers, as you maybe you remember, can store far shorter, far less significant digits. So the accumulation of the errors can appear much earlier in your code, yeah, and you have to take greater care about accuracy. Yeah. So in engineering fields, typically we stick to double precision numbers. Yeah. Try to mitigate those issues. Yeah. With those accumulating inaccuracies. Yeah. We won't face here, I think, any kind of the problems that can rise to this, but it's good to know. Yeah. So for double precision numbers that we are here, that they store about 17 digits of real number. Yeah, 16, 17 digits of the real number are stored properly using double precision numbers. Yeah, and so if you just put those numbers directly into the computer, at most 16 of those digits are correct. Yeah, so let's run this code to see this. Yeah. Yeah. And now you can see here why this kind of evaluation is incorrect. Yeah. Because if we type 001, yeah, we have those 16 that are correct. So that this is 1 and many zeros. But at the end, you have this small, error that is shown here as 1. Yeah. If we print 0.2, same story. Mostly it's fine, but at the very end, there is this small error. Yeah. So when you add those two numbers together, you have the representation that is almost correct, but it has this small error at the very end. Yeah. And here is the problem. That it's also, okay, so when you just print 0.3, it's just slightly different number. And now you can see that because of those small errors here, the closest number that can be used after adding those numbers is that one. It's clearly that one, yeah? But if you want to just represent 0.3 in the most accurate way, the second number is slightly more accurate to represent 0.3. The difference is very small, but if you compare them like that, they are clearly different numbers. Does all this make sense to you? Is it clear why it end up that way? Yeah. And if we just print 1, 2, and 3, it was correct because it's much easier to represent those numbers. Yeah, it's just 1 and bunch of zeros, 2 and 3. Yeah, so that's why this matches perfectly. Yeah, of course, most likely there are some cases that will work perfectly fine, like 0.2, maybe 0.4. I haven't checked it. Yeah. Yeah, but it rather has tendency to accumulate. Yeah. So it's the same story, so double. Yeah. Well, I shouldn't expect it to work, to give true. Yeah. This is the case. Yeah. Also, here between those two numbers, yeah, there is this concept of machine epsilon. Yeah. So how close can be two numbers to each other? Yeah. And here, between those two numbers, there is no number that you can represent. Yeah. So either it can be this one or this one. Yeah. Does it make sense? Because those numbers that changes by 1 bit on this whole length. Yeah. So there's no way that within the representation you can fit any number in between. It's good to know. Yeah. So this is important for our testing. Again, for most practical application, it's not a big issue. Sometimes it's an issue, so good to know about this. And yeah, this is the story. Any questions? Does it make sense? Is it clear? Okay, what doesn't make sense?
For instance, that this arrow at very end is still like always the same, or is it sometimes different? Like for instance, for the first one, 0.1000 at the end 1 can also be another number at very end.
No. No, at least if we consider, okay, so yes and no. Yeah. So we have some standards for those representations. Yeah, and all modern processors and computers follow specific standard. Yeah. So if you are in this specific standard, yeah. So in general, in the architectures, it's always that. Yeah, because if you want to get some more details, yeah, you can always go to wiki. Floating point arithmetic. Yeah. Maybe not arithmetic, but so here you can see, for example, those standards. Yeah. And for example, here you can see how they are stored. Yeah. So they are stored like sign bit. Yeah. So you have just 1 bit provided. This is single precision, but for double precision, simply the fields of exponent and significant precision are larger. Yeah. So firstly, there is standard to represent them in certain way to be sure that it matches between the vendors, yeah, and for the storage. So sign bit, so plus minus, yeah, this is 1 bit is used for that. Then you have exponent, and then you have precision, yeah. So all those numbers are kept in this. Here is the representation, yeah, in that way, yeah. So just a bunch of bits, of course, yeah. And here you have a fraction, And this fraction is just that part that tells that about 17 digits of real number is stored. Yeah. So if you convert it to decimal point from binary to decimal, yeah, you will get those around 70 numbers stored. Yes, that 16 can be correct. And then you have exponent. Yeah, so that's why you can just range. You know, you can work with different ranges thanks to this. Yeah. So despite the limit number of the decimals that you can store, you can calculate both 10 to the minus 100 and 10 to 100. Of course, if you subtract those two numbers, you get garbage. Yeah, so this is one of the source of inaccuracies. Okay, does it make it slightly clearer? Yeah, and with this representation, so always when you point 0.1, because of the standard, it will find what is the closest representation for 0.1, yeah, and it's always the same set of the bits for the given standard. So it always manifests in the same way, yeah. So those are the closest representation, but that provides the numbers, yeah. And then this is just result of adding those bits, yeah. And so this is the closest number as well, because even you can see that 1 plus 1 doesn't give 4, yeah, but this is the closest you can get. And still, the closest number to 0.3 is 1 bit off, yeah. So this is the classical accumulation of those rounding errors. Yeah. And because number of those bits is limited, simply, and those operations are very simple, this causes that, you know, between those two numbers, so that one and that one, there is no others, because again, they just differs by 1 bit somewhere. Okay, make it, okay. Yeah. Yeah, so it causes small rounding errors. In final results, we have seen it. So if we cannot make tests like that, what should we do? Yeah. And also here we have this simple quiz. Yeah, I hope that most of you have already time to answer it. Let's give, you know, maybe half a minute for the one that, you know, haven't noticed it. Which of the following statement is true about the floating point representation of the number 0.1 in binary? Okay, I think that the time has passed. To the nearest integer in floating point representation, it's not. Integer would cut this 0.1, so it cannot be integer because integers are stored differently. Yeah, but cannot exactly represent in binary floating point. Yes. Yeah. Okay, perfect. So, because we cannot compare the numbers directly, is a rule of thumb that if you compare results of any algorithm that use approximation, and here we have already, like in numerical integration, two sources of errors. One source is inaccurate representation. Second source is just approximation of the algorithm. Yeah, we are testing the error with respect to a tolerance. So we need two values, yeah, value that we expect to get and value that we get from our computations, yeah. Then we subtract, well, then we calculate the error between those two values, yeah, and we expect that this error is small, very small, yeah. So like if we have this example of A, B, and we expect to get 0.3, then we can compute a plus b, and then we can calculate this error, which is the difference, absolute difference, because it can be positive or negative, so we have to take absolute value of it. Then we define some tolerance, and then we calculate it. Yeah. So when we run this type of the code, so okay, let's clear the stuff. A equal 0.1, b equal 0.3, and then we get we are expecting to get 0.3, but we know that a plus b doesn't equal to expected, yeah. But then we can get computed value as 0.1 plus 0.2, yeah. And then we calculate the difference between those two, ABS of computed minus expected, yeah. They look the same because we cut those the last numbers here. So if we round them up, they look the same. But of course, we get this small difference, yeah, at the range of 10 to the minus 17. But then we can set the tolerance 1 minus 15, and then check that simply if it's smaller than tolerance. And then we get the desired value true. So why did I choose 10 to the minus 15 for tolerance? Yeah. But why specifically that one? Yeah. Okay, so part of the answer is here that because it can store around 16 correct decimals. So if we are making calculations around 1, yeah, around number 1, the tolerance that we are expected is 10 to the minus 16. Yeah? Make sense? Yeah. So 10 to the minus 15 is slightly, it's in this range, is slightly more conservative. Yeah. By the way, another way to get it is APS. Do you know this function APS? Yeah. APS provides you this machine epsilon. So this is the smallest number. So if you add 1, because EPS by default works with 1, yeah. So if you add 1 plus epsilon is the next number. You cannot have any number between 1 and 1 plus epsilon. Again, the same story because of those limited number, yeah. And for each number, yeah, you know that you can just store the number here and the next one because of those bits, yeah. And APS can tell you what is this difference, yeah. So and then if you use APS and multiply it by, for example, 100, this is also pretty good tolerance value, especially if you are out of range of 1. Yeah, another way is just to use relative tolerances. Yeah, so relative tolerance, it means that if you have the numbers of different ranges, yeah, so I will skip maybe running this code, or maybe not. Okay, it's super short, so let's run it. Yeah, and it's just here. So just copy. Yeah. So it shows that as K10 is simply the values of the next powers of K. Yeah, so 10, 100, 1,000. Yeah. And this shows that if you run something like this kind of subtraction of some numbers with different ranges, you sometimes get exact values, but in general, those tolerances are totally different because we are changing the ranges. Yeah. So we cannot use one universal value of the tolerance for all our calculations. Yeah. But we have to either use epsilon, yeah, that will calculate our machine epsilon in proper range, or we have to use relative tolerances, yeah, So in relative tolerances, simply we can, instead of having this computation, yeah, we are dividing this by K10, the range of our values. Yeah. So we are just normalizing it. Okay. Yeah. We are just normalizing it, and then you can see that for all the stuff that doesn't cancel out because of when those random errors, just match up, we get the values at the range of 1 to 10 to the minus 16. Yeah, and this, of course, corresponds to the fact that, in double floating point numbers, we can store up to 60 numbers. Yeah. Yeah. Makes sense? Does all this make sense? Yeah. Okay. So,
I must show like of the minus the power of minus 16, but still not equal, right?
could you repeat because I wasn't.
The powers, the numbers shown in the MATLAB,
Yeah.
although they're now like very small
Yeah.
differences, they're still not equal. So we still have to do like B.
Yeah. Yeah. And of course, in general, the more complicated algorithm, the larger those errors are. Yeah, but they should be limited. Okay, so as a quiz, we have this one number here. Yeah, what is the machine epsilon in the context of floating point arithmetic? I hope it's clear. So if you haven't answered, let's give like 30 seconds. Okay, so nice. Okay, so now it's a big question. Do we need a break? 5-minute break? Is it okay? Okay, so we'll see in 5 minutes. Yeah, maybe I will refill the coffee. Okay, still no questions yet, so see you in a few minutes. Okay, welcome back after a short break. Yeah. So the next part is unit testing. Yeah. So I suppose that in some old days, those CS guys debated how to make those tests. Yeah, it's easy to write, but easy to forget, and somehow how to keep them working. Yeah. So they came up with idea of writing so-called unit tests because you can have various types of tests. You can have unit tests, can have those system tests, you can have some benchmark tests, and many others. Yeah, we won't go through it. Yeah, we'll use the just that part. Yeah, so one of the thing is that it's just easily available in MATLAB. Yeah, MATLAB has built an unit testing framework. Yeah, which makes just our life much easier. Yeah, and it's extremely popular. Yeah, so I think that in most of the languages that you can came across, yeah, you can have it available easily. It's in Python, it's in Julia, it's in C. Yeah, I have even seen one in Fortran. Yeah, despite for yeah. So yeah, the idea of unit testing is to test units. Yeah. What is unit? Typically, unit is just why it changes. Okay, I can imagine why it changes. Laser pointer, yeah. So, to test small pieces of larger code individually, yeah. So it's to abstract your code from the surrounding, yeah. So you identify a small unit of the code and then make tests for this unit, yeah, several tests. So what is unit? It depends, but in this kind of engineering practice, yes, it's typically a function, yeah. So the functions should be relatively small, like here the function is just to integrate things, yeah. And then for those functions, you can write tests that verify that those functions work as you expect them to work, yeah. So then the premise is that when you run the small code and it works properly, when you start incorporating this code in larger project, yeah, then the tested part won't break your project, yeah. So it also yeah, so it works that way, yeah. So if you incorporate unit testing in your development, firstly, you have to write functions, yeah. Typically, you keep the functions separate, so they are pretty small and manageable. Unit tests are typically far better documentation than any comment because in the unit test, you are showing explicitly how to use your code, yeah. So if you forget after a while how this function is intended to be used, you can open unit test that is associated with this function, yeah, and then you can see some examples that you can copy paste to your other code with direct usage, yeah. So unit tests should be standalone, so they shouldn't, and they cannot, I think, easily. Of course, in programming you can do whatever, yeah, but they shouldn't depend on the runs of other tests, yeah. So small units, independent tests. One algorithm is considered as a unit in scientific programming. The challenge is to deal with numerical approximation errors. That's why we discussed this, because we have to make those tests. We make those tests automatic. Yeah. So after you have your program, yeah, you just run one command. At least this is the case in MATLAB. Yeah. Yeah. And many IDEs support this. You just run one command. Maybe there is something on the ribbon. Yeah. Hit enter, and then all the tests are run, and you get the summary with the hope that you will get at the end that 0 errors were found in your code. Yeah. So maybe you are ready to deploy. Maybe because still, often in a large project you have to test it. And unit test, a side effect of unit test, not a function, forces programmer to modularize code. Yeah, having modular code is always, almost always nicer and more useful. Again, the simpler code, the better. Yeah, and the more modular code, the better. Yeah. Fancy codes are for also for some competitions typically. But okay. And here we have some. Okay. So any questions to unit test? Does it make sense? You have some unit like algorithm, like our function trapezoidal, and then you can write function that is, or the code, we'll write it soon and learn how to do this, that it's can be done automatically, that tests this code. And then we try to verify that our implementation is correct, that our algorithm is correct, that behavior of this algorithm is according to some theoretical or theoretical assumptions. Yeah. Yeah. Okay. If it's clear, yeah. Okay, because I prepare extra 2 questions. So what is the primary purpose of unit testing in numerical computations? To speed up the execution of the code, to verify that individual components of the code functions methods work correctly, to ensure the code uses the least amount of memory, to automatically optimize numerical algorithms for better performance. Okay, 20 more seconds. I think that should be already done. Yeah, exactly. Yeah, optimization of the code and optimization of the use of memory are different tasks. Okay, and next question. Which of the following is the characteristic of the good unit test? It should test multiple functions at once to ensure efficiency. It should be written only after the entire program is complete. It should test a single piece of functionality in isolation. It should rely on external resources like databases to verify results. So again, 20 more seconds. Okay, I think that we are done as well. Yeah, yeah. The first one is not the correct approach. Yeah, you shouldn't ensure efficiency in the early stage, and when you have entire program, it's typically then it's hard to incorporate unit test. Yeah, so it's far better to start from the scratch when you want to do this. Yeah. Okay, perfect. Writing test functions. Okay, so now we are talking specifically about MATLAB approach for unit testing and how to write. This is just one way. There are many, a few others, yeah, but this is the simplest way to write test scripts, yeah, in MATLAB, and ensures that they are just verified properly, and then they can run for automatic testing. Automatization is always nice in programming. Tests can be run by a programmer or they can use test frameworks. it's always better to use test frameworks. Yeah, you don't want to rely on this. Yeah, typically, preferably you have some even continuous integration system connected with your version source control. In the way that you commit your code, you push it somewhere, yeah, and then it's tested. So then on email you get results. All tests were passed. And I think that in any reasonably serious, software development company, and as we know now, almost every company is software development company by part. This should be done that way. But okay, we will push tests in separate test scripts. Yeah, yeah. So there are also test objects, test functions. We will use test scripts. Yeah. So firstly, it's important to name them properly. So that's why by going through the code, yeah, this framework can find the piece of code that are tests, yeah. And because in MATLAB everything is about the files, yeah, so you have to name files properly, and the name must start with test underscore. At least we will use this. Yeah, I don't remember if this underscore is critical or not. It must start with test, yeah. We'll use test underscore. Yeah. So for example, to test trapezoidal, we use test underscore trapezoidal M. And then we know where to find our test for trapezoidal method. Test must be a Boolean expression B. Okay. So we have to have this Boolean expression, yeah, and we want it to be true. And this is the part where we get into those comparison with those differences. Yeah. B must be tested with assert. Okay. There's function assert that will assert that this value is true. Yeah. Test fails if B is false. So this is the way how you know that something is wrong, and it will be communicated to you. If everything is fine and B is true, nothing will show up. Yeah. A message yield is optional information printed when B is false. Typically good to add. Yeah. Of course, you can always refer to the file, see it, yeah, but it's good to add some message information together with assert. And you can use some formatting even there. For multiple tests, each test must begin with a line starting with double percentage sign. Yeah. So it means that you can put many tests at once in single file. So you don't have to write test 1, trapezoidal 1, test trapezoidal 2, because typically you have multiple tests and you can gather them in one file. And then can start with just MATLAB sections. You know this concept of MATLAB sections? Yeah, maybe it's not super crucial, but if you put 2% signs, you'll start new section. After following the above guidance, you can run all tests with run tests. Okay, there's command run test that, as name indicates, it run tests. Okay, we have one short question about this. Which MATLAB function is commonly used to create a basic unit test for a function? Or results of this function. Yeah. Okay, let's see. Any questions, comments? No? Perfect. $15 seconds to go. Close. Yeah. It was assert for tests. Yeah, test is just convention to name the file. Okay, example. Yeah, so we'll make this very simple example of writing tests. Yeah, based on the thing that we have already done. Yeah, so this is just to show the test. Yeah, so the example is, let's say it trivial, to say the least. Yeah. So we'll create a new, okay, let's call it script. Yeah, add that will contain function and function this type, as you can guess by the name. Let's do not make any jokes. Yeah, it just adds two numbers. Yeah. So it adds A plus B. Yeah. So I suppose no comments needed. And now we have to add test. Yeah. So first thing is that we have to name it properly. Yeah. So again, name will start with test underscore. Yeah. And then we'll indicate which function we are testing. So test add. Yeah. Okay. And now with this, test add is just a script. Yeah. We'll put here two tests. Yeah. So we will use this convention of MATLAB sections. Yeah. So if we put here two percentage signs, it starts the new section. Yeah. And we can put a comment here already. Yeah. Test if 1 plus 2 is equal to 3. Yeah. In standard arithmetic. So we get that A is equal to 1, B is equal to 2, and expected is equal to 3. Okay. And now we can get computed is we call our function add with 1, 2. Or maybe A, B. It should be AB because we already get those things, yeah? And then we can write assert, yeah, as pointed out to test the results. And we can write assert that expected is equal to compute. Here we can use this comparison because we know that the whole numbers, it works well, yeah? So this is for the first approach. And then we can write a message that, and we can put this message error in computing 1 plus 2. Yeah. So this is the sum test. And now we can verify if this test is discovered and if it runs, yeah, in different way. So first of all, what will happen? How do you think? What will happen if I will run this function, this script directly? What we will see?
Nothing.
Yeah, exactly. Like a good test, we will see nothing. Yeah. So if we just run it, nothing. Yeah. This is what we are expecting to get. Because this is the behavioral proper test. Yeah. Test passed, nothing happens. Yeah. This is pretty typical. So we now run tests as pointed out on the slide. And now it takes a while for the first run. So it's nice also because after running the test, it's good for just testing. That when we, for example, write this function, we can run specific section and see if the section, behaves properly. Yeah. Run test gives us those extra information. Yeah. So first of all, it tells us that it figure out that there is this special file called test add, and then this dot shows that we have one test inside. So it runs, if we have more, then there are more dots. Yeah. Then done. And then it shows some summary, especially here. So it also stores some object. You can use it for other purposes, but it provides here this overview that one test passed, 0 failed, 0 incomplete. So we are happy with this result. All tests are passed and some execution time. Yeah, because of GIT, second run, it's much faster. Yeah, and if we use semicolon, we just get, we don't get the summary. But okay. Okay, so this is the way it works, yeah. Now we can add those second test, yeah. So we add, if you want to add second test in this kind of function, we just add second section, yeah. Test if 0.1 plus 0.2 is equal to 0.3. Yeah. And yeah, we follow the same procedure. So A is equal to 0.1, B is equal to 0.2. We expect to get 0.3, yeah, and the computed value is add AB, yeah. So let's forget for a while what we have learned a while ago, yeah, and we will copy paste this basic test that expected is equal to computed, yeah, and it will show, and we updated just the message, yeah. And now, so first of all, if we just run this section, do you remember what is the shortcut to run section? Run section shortcut is, okay, cool. So let's run this section, yeah. Yeah, so first of all, we can just run section, yeah, with here command enter, or I suppose it's I think control enter in Windows. And first of all, when something is wrong with the test, we get error, yeah, because assert if the first Boolean value that should be true is not true, rises error, yeah, so it shows error, and then it shows this message. Okay, so this is clear indication that it doesn't work. Then if we run tests, so we have few things more. So first of all, first test was run without issues. This dot indicates this. And then it shows that we have error. Where is this error? Yeah, you can go there directly. Down tests, yeah. And then our summary shows that one test passed, one failed. Yeah, so we have some failures. So we know what to do. We will fix this test because we know that this is because of our incorrect comparison. Yeah. So we have to calculate the difference. Of expected minus computed. Yeah. So and now write that we need the tolerance. How to get tolerance? How do you want to get it? Yeah, we can get APS of A times 10. Yeah. Okay. So I showed that APS can be called like that, yeah, but it can be called also with the argument, yeah, and with the argument that it shows what is the closest number to this argument that you can add, yeah. So then it's slightly better to use this because then we don't have to use relative tolerances, or we should use the relative tolerance and just use a APS of 1. Whatever works, yeah. I hope. And then we want to write that difference is smaller than tolerance. Now I press Control Enter to run this section. As you can see, nothing has happened, yeah, as expected. Yeah, not CC. And then when we type run tests, running test add, as you can see now, it found 2 tests in this, and then 2 passed, 0 failed, which is of course nice. Okay. Any questions, or is it clear what are the principles of writing and running tests in MATLAB? Any questions to this procedure? Is something unclear? Okay. No questions? Let's move on. Okay, so now what we want to do with what could be a good test procedure for algorithm. Yeah. Here are three good ways to test if the implementation of numerical method is fine. Yeah. So first thing is to comparing with hand computed results. Yeah. So you know what is the algorithm. Yeah. You have coded it. Yeah. And you just and then you try to solve it kind of by hand, and then put the numbers there, some exact values. Use very small n. Yeah. Because here the task is not to check if it converges or provides good results, but if it replicates nicely the steps that you have taken. Okay? So for example, for our trapezoidal method, we can use run trapezoidal method on some non-trivial function with just 2 steps. Yeah, then you can just directly, put this algorithm on hand, then use calculator or even MATLAB to get those numbers. And test if this number is just the correct one. Yeah. Next one, if possible, could be that you solve a problem without numerical errors. Yeah. So without those approximation errors. For example, trapezoidal rule must be exact for linear functions. This is clear. Yeah, because it approximates everything with line. So if you try to integrate linear function, you'll get exact results. Yeah, up to numerical precision. Only rounding of errors can appear. Yeah. So produce error should be 0 to machine precision. Yeah. And then third one, very nice ones, it demonstrates correct convergence rates. Yeah. Because typically when you have algorithm, it has some convergence properties. Yeah. So it means that how fast it gets into proper result. Yeah. So it's known that for trapezoidal and midpoint rules, it's known that the error depends on the second power. Yeah. So if you double n, the error should be roughly 4 times smaller. Of course, there are still some constant terms. Yeah, this is just by omitting those constant terms. But for large n, yeah, that's why it's written that for n to going to infinity, so that those lower order terms doesn't matter so much. So for large n, this should be achievable. Yeah. Okay. So first test. Hand computed result test. Okay, so you don't have here pen and paper, yeah, but here is the pretty exactly calculated result, yeah. So we have already done this more or less, but not in the systematic way of writing tests, yeah. So for this example, yeah, if we just use 2 trapezoids, the calculations is like that, and the number is like that. And so we can compare it with pretty high accuracy. Yeah. So I wish you to write test trapezoidal M file, yeah, to test trapezoidal. Put their first section, name it like test for hand computed results, yeah, or whatever, and then use this as exact value, then compute the value from the trapezoidal method implementation you have, yeah, and check if test works. Make sense? Any doubts? What is required from you? Do you know how to make it happen? Hmm?
Just the two trapezoids.
Yeah, so it's trapezoidal method. So it's to test trapezoidal. Here you have also the reference. Okay, let's try. If you won't try, you won't know.
And that's always section. Double first understand. The way to check again. It's not it. The A, we have to be in the error message. And that's it. Yeah. I don't know if you're.
I was fixing the trapezoidal function. I think it's called. So,
I'm cannot. Function in a script function, so we cannot.
yeah, but I can use this one.
Yeah, to save it as a file, then, yeah, it's a function, and save it, yeah, then, this is the correct one, exactly. Okay, and now we can write it as this function. That function. Outside of one. Yeah, okay, maybe 4, yeah, but that's fine. It's fine. First, that was so much lower here. But okay. Which is, I wouldn't complain, but it's not so. That's what I have. It's bunch, huge code here. And also the testing, that's very good. Code is like, should be like a story. listening to you guys. And that is also feel that nice. Yeah. That's should have read very about this. Also, you should do very expected tolerance. That become our close for numbers. Even if you both say it's always a bit heavy. Because you can just make a very small change to trapezoidal, like change the order of computations, maybe. Yeah, it's tolerance.
But it's just it's open here, the next week.
Yeah, it's What was here is not. Yeah. Shaded, just but it's just that if you go into my this thing, that also they can listen. Or shouldn't be this. Okay, good. The whole station. Everyone can use the issue, but it should be one. Yeah. But it comes to the end of the but if it's very expected, that's good. Without these two. Anybody who use from numbers, you always expect zero. But you're not expecting to be 0, 0. Yeah. And 0. Yes. So we will do it for different and why you are using the same, that's fine. I think what's the line about this? Some binary funds or some XML file. It's hard to read them. But okay, and does it work with those next files if you run test? It's hard to execute it. But don't send it to next files. And okay, I have also one comment about this assignment that I ask you to send two files, PDF and zip. Okay, two files.
PDF and zip.
And zip, yeah, and sign.
Zip is a PDF.
No, 2 files, PDF and zip. Yeah. I have to be more specific. Yeah, of course I can download it and zip, but then I have to download it and zip. And when you send PDF, I can just take a look on PDF. And this is 90% of my evaluation.
Did you get to include the old code?
Yeah. I'll be more specific for the next time. But okay.
We will get to even very soon to this assignment because you will get the second one soon. But okay. Any questions to this task? Many of you have solved it, yeah. But yeah, should I quickly solve it, or you know how to deal with it? Yeah, because I've seen that many of you have coded it. Yeah, so yeah, it's just, I suppose, matter of just putting it together. Yeah. Yeah. So for the next test, yeah, problem about numerical errors. Because we are, again, those are typically approximation methods. Yeah. But when we know how they work exactly, sometimes like here we can find the problems that has just round of errors, no numerical errors. And one of those errors is, one of the case here is that if you use linear function, if you integrate linear function, yeah, because we are approximating lines, the results should be exactly the same, yeah. So we can use function like that, yeah, that use some not very standard numbers like 0 and 1 that can by accident hit some neutral element of multiplication or addition, yeah. That looks a little non-trivial, you know, and calculate it, yeah. And we can also typically calculate it quite easy by hand and then check results, because it shouldn't matter if you use 1 trapezoid, 2 trapezoids, or 100 trapezoids, you should always get the same result, because there is no numerical method. The same with respect to accuracy, yeah. So because we are heading to the end, we have just like a few minutes, so maybe I will write this test, yeah, to be sure that everything is clear, yeah. But it follows the same rules as the previous one, yeah. So use this, yeah, to write the test. Perform computations with 3 different values of n, and functional antiderivative is just like here, yeah, and verify that it works, yeah. So because I haven't done it yet, so I will create a new file that it's called test. Test trapezoidal, yeah. I'll use this, yeah, standard approach with sections, yeah. So no. Okay, nice. Okay, so our function to test is 6 times x minus 4. Yeah. A is equal to 1.2, for example. B is equal to 4.4. Antiderivative is 3 times x to the power minus 4 times x. Yeah, so this is our antiderivative. So expected value is f of b minus f of a. Yeah. So this is the preparation for the test. Yeah. So I just define the test. Yeah. So what to use, other variables that are needed to execute it, and then I calculate the expected value. Make sense? Yeah. So because it asks to, okay, it's written here, computations for the 3 different values of n. Yeah, so computed one can be trapezoidal on the function from a to b with how many? 1. Okay, 2. Let's see v2. Yeah. So with 2. This is good. 1 is also nice because it's a good question if it works with 1. But okay, it's another test. And then we can compute error 1 is equal to ABS of expected mean minus computed 1 We also need tolerance for all this. Yeah, so tolerance is APS of expected. It's always better to use expected than computed, because at least expected it's something that we know it should be in the correct range, and computed could be off by far. Yeah. Let's use by 10 times 10, because it's pretty simple computation. It should fit into here. And then we write our first assert, then error 1 is smaller than our tolerance. Yeah. Some description. And then we can make the first run to see. Okay, no errors. So it's a good sign that maybe we have done it correctly. And it asks us to run 3 times. So let's copy paste it 2 more times. So error 2. Okay, yeah, we have to yeah. I forgot about this line. So computed 2 will be with, let's say, 87, because why not? So use here computed 2 and use it error 2. Yeah, you have to also, of course, care about the correctness of the error. With copy pasting is always a risk. And computed 3 will be with, so how many trapezoids? Okay, it's simple method, so it can be 1000. Yeah. Error 3, computed 3, assert, and with 1000. Yeah. Let's save it. Let's run it. Okay, nothing. And then the proper way. So we have done all those 3, verify if your test works. So we just run it. It doesn't throw error. So this is a good thing. Yeah, but just run. Okay, I think it's fine. Yeah. So it run this test at that you write area and run 2 tests. Fine. Yeah, no surprises here. It's also fine to test trapezoidal, run 1 test. Yeah. So it doesn't count the number of the asserts. Yeah, it just found the test. Yeah. But yeah, 3 pass, 0 failed. So test runs works. Okay. Question, comments? Anything? Okay, perfect. So about convergence rates, yeah, I think we are already running out of time. We have like 1 or 2 minutes, yeah. But convergence rates, just check, yeah. If, as we written, as n grows, errors drops in the second power, yeah. So it's written here, yeah, trapezoidal rule, when we double n, error is reduced by a factor of about 4, yeah, because square 2. So if we the number of n it's tripled, so it should be the error should drop by 9, and so and so. So error of numerical integration using this method usually converge to 0 as n to minus p minus p, because it's when n grows. Minus is because n grows, then errors drops. Yeah. So we assume that the error depends on n using this. Yeah. So there is some constant value. There's always some constant value, and n to r. Yeah. And r in our case is -2. And using this assumption, we can run those tests, for example, for different n's, because the convergence rate, it depends between different runs of the same algorithm. Yeah. We don't need to have any specific real value. We use the different tests to verify this. And following this assumption that the test goes into the error follows the equation C and R, yeah, we can, while having two tests for different number of n, we can figure out that R can be calculated by using this equation. Yeah, this is just transformation. And then we can verify that R is around 2 or minus 2. Yeah, it's around minus 2 when n is sufficiently large. Anyhow, understandable? If it's not, then we can, of course, follow it. We can for the next time. But yeah, here is this another test, convergence rate test, to run it like that. Yeah, so we have to select two different values of, or several different values of n. Yeah, for example, you double the n, at a certain point of this doubling, yeah, the R will be as you expected. So around the integer minus 2. Okay, yeah, but we won't solve it because we are run out of time. So final remarks about testings. It's always too good. Yeah, there are like two landmarks of reasonably of reasonable start of any programming project. One is to have test, and also it's good to have version control system. Do you know any kind of version control systems? Do you know what I refer to? Yeah, have you ever used it? Okay, perfect. Okay, and I have an assignment for you from numerical integration test. So it's very similar to the last one. Yeah, there are some exercises to be solved in the book. Write a report. Okay. I think it doesn't make any difference for you, but it makes makes my life easier when this is done that way. Yeah, because of the way how Moodle works and other stuff. Okay. Any questions? Any comments to the last assignment?
You have to perform at the end of the second exercise in the assignment. At the end, it asks to perform a check to see if the number are being sorted correctly.
Yeah.
We have to perform the check with this test algorithm.
No. No. Test. Writing unit test is just, task of writing unit test. Yeah, it's separate task. Yeah.
Okay.
So check. So, if you have 10 numbers, you can just take a look on them. Yeah. So, yeah.
About usage of AI. I read the email, but also if we use AI, we can still achieve the maximum point, let's say, or is a way to, I don't know, if we use AI, we increase our score.
No.
Is there any formats for the reports?
Yes. 2 A4 pages. Okay. So about this 2 A4 pages is maximum of 2 A4 pages of text. Yeah. So if you have some figures, so it's always good to put some figures, yeah. So if you have trouble with fitting those figures on 2 A4 pages, yeah. So because I believe that all those reports should be at max 1 page of text plus figures, yeah. But if you have it very hard to fit into those 2-page limits, it's okay to be more, assuming that the more means you just add more figures, okay. And any format, yeah, and you know, it should be signed, I suppose, yeah. So it's good if you have your name on this, yeah, because it's your report, yeah. The only requirement that I put just like you know, in the email, yeah, that you know, that please make this statement if you use or do not use AI, yeah. It doesn't count if you already submitted the report, it's okay, yeah. But if you submit it from now on, yeah, put this claim, yeah, I use it or I do not use it. And when you use it, you have to report it very detailedly. Yeah. But there is no specific format. Of course, following this standard like introduction methods, some results and conclusions, it's preferable, yeah, because it's in engineering, it's very common, yeah. So I would assume that typically you need a good reason not to follow it. But that's all, yeah. Or do you have any more specific questions? It's plenty. 2 pages of text is plenty. Put in code? Nothing. Do not. It's up to you. Oh, it's advanced master course, master level course. Yeah, most is up to you. Just do not put any code in the report. Code is that's why you have report and code, yeah, because there is no reason to put any code. Okay, you can put a code if like one line, yeah, that you know this line is. I would like to highlight this line, yeah, but not like you know listing of the code or something like that. No. So explain it enough details, but not more than needed. You can always then resubmit your report if you are not happy with what I give you as a grade, and if you want to improve based on my comments. Okay, so if there is no extra questions about the assignments, like typically, when I will have some free time. So today, at latest tomorrow, I will put all the materials available for you. Yeah, so I will try to do this as soon as possible. Yeah, and we'll meet next week. Okay, perfect. So great. Thanks a lot, and see you.